So we saw Plot 3D and the functionalities with Plot 3D. Um, let's say we want to plot multiple surfaces instead of just one of them. Say we want to plot in 3 dimensions x squared plus 2x plus y, x squared plus y squared, and sine x plus cosine x. And we want to specify limits for the x and y axis, let's say -5 to 5, and y coordinate -5 to 5, and we get an error. And the error here, if you pay attention, you could see that we have to specify the functions within a particular range. So, within a list. So, what I'm going to do is I'm going to change that to a list instead. And this time I have a picture. It's quite weird, but that's what we have. And so we successfully plotted the 3 functions in the list. And all of them are plotted for x values at -5 to 5, and all 3 surfaces are plotted from -5 to 5 for x and -5 to 5 for y. But what if I want to plot the first surface from -5 to 5, but the other 2 are between 0 to 2 pi? So I would have x squared plus 2x plus y, and I am going to specify, well, we have to define a global list for all 3 elements. So I'm going to define that global list. So I open the list here, ended there, and that is my first expression, and I'm going to specify the limits for the first one. I want it between -5 and 5 for the x-axis, y between -5 and 5 for the y-axis. Now I move on to the second expression, which is x squared plus y squared, and the third expression, which is sine x plus cosine x. So I have all 3 expressions defined within the function, and now I'm going to specify a global range from 0 to 2 pi for x, and y I'm going to do the same thing, 0 to 2 pi. Forgot to put a 2, and this should be 2 times x. And I still seem to get an error. So let's see where we went wrong. This should work. Perhaps I made a mistake somewhere here. So the square bracket was in the wrong place, and I'll explain that one more time. So, so now you can see three surfaces. So what we did here is we had the first expression, which is right over there, and that is from -5 to 5 for the x values and -5 to 5 for the y values. The second one is the second element of that list, and it is x squared plus y squared. And the third is sine x plus cosine x, still is part of the third list, but the x and y coordinates corresponding to the other two functions must be inside the list, like so, for us to plot it. Let me show another example here so that we are clear. So I'm going to start with the list. I'm going to define my first function, let's say x squared plus y squared. I'm going to give the x and y bounds, so x is from -2 to 2, and y is from -3 to 3. So that is our first function. The second expression, I'm going to define it to be simply x cubed plus sine y, and the next one I'm going to define it as x times cosine y, and I have to specify the limits. I'm going to specify the limits as x from -2 pi to 2 pi, and y is from -2 pi to 2 pi, and enter, and we get that curve. So we should see that there are three different palettes here, and that would correspond to three different surfaces that we have. So now, what does it mean? So the limits here, x -2 to 2 and y -3 to 3, apply to x squared, y squared, x squared plus y squared, whereas the limits -2 pi to 2 pi for x and y apply globally to both x cubed plus sine y and x times cosine y. Now, what if I want to give another range, local range, for one of the expressions? So let's start with the first expression, which is x squared plus y squared, and I have x defined between -1 and 1, y defined between -2 and 2. So that is the global list. So we are ending the first element here. So that very first line right here has a parentheses and a square bracket that corresponds to the square bracket and parentheses over there. And in the first line here within plot 3D, we have the expression followed by the x range, y range, and keep in mind we have to close that because the entire thing over here corresponds to the first expression. So comma, I want to define my second expression, which is x cubed plus sine y, and I'm going to give its own unique range for x and y. And lastly, I have the third, which is x times cosine y, and I am going to let it have a global range, which is x comma negative 2 pi to 2 pi, and y is from negative 2 pi to 2 pi. Let's see if this works. It did, and that's what we have. So you can see that there are three surfaces corresponding to each of those expressions that we had, and they are defined at different limits. So the first one is defined from negative 1 to 1, the other one is defined 0 to pi over 2, and the last one is from negative 2 pi to 2 pi. So which is why you get three different surfaces, and if you rotate it you would see all three. So that's surface 3, and that's defined from negative 2 pi to 2 pi, and that is surface 2, which is defined from 0 to pi over 2 for x and 0 to pi for y, and that would be the third surface, and it is defined from negative 1 to 1 for x values and negative 2 to 2 for y values. Now, so what if we define our own function? Let's say we declare a function or define a function of our own, and let's say it has two values, f of x and y, and we define that function to be x times sine x plus y times sine y, and we want to plot this function. Clearly this function is dependent on two variables, so the value of the function is going to be plotted in the third axis, which is the vertical axis, or the z-axis. So how do we plot it? We simply say plot 3D f of x comma y, and we specify the range for x, let's say from negative 2 to 2, y from negative 2 to 2, and let's get rid of the mesh lines. And we'll specify a grid. Let's see what happens. And that's what we end up getting. So we could have a user-defined function and end up getting a 3D surface plot. So that is the plot that corresponds to the function f. So what if we have two different expressions, let's say f and g, and we want to plot it in different areas of the xy plane? So let me define a function g of x comma y. I'm going to define it as x times cosine x plus y times cosine y, and that is my next expression. So I'm going to use or combine the idea that we learned earlier, where we could specify local ranges to each function and extend it to the functions f and g. So plot 3D, so we need a global list, and we need a list for the first function. So that would be f of x comma y, and define the range. Perhaps I'll do it between negative pi and positive pi for both x and y. And we have our next element in the list, which is g of x comma y, and that is going to have the global value. Let's define it between negative 2 pi and 2 pi. And we will get rid of the mesh lines color and give grid, and we end up getting that. So both of them are plotted here, but we're not able to see clearly because of the range. Perhaps we could create a divide and make it so in non-overlapping ranges. So we'll do negative pi, and we will do pi to 2 pi. Interesting. Oh, interrupt here. I wanted to stop, or else this is going to keep on going. So sometimes when you choose the axis, you've got to be careful, or else we wouldn't be able to plot the surface. So that's exactly what happened here. So let me evaluate f and g and try plotting it over there and see if it works. Still doesn't work. Let me try something here so that there it is. So now we end up having two different surfaces, one corresponding to F, the other corresponding to G. So what did I do? So what I did here is I split G and F and assign them individual ranges. In this sense, so I have F, that is the first element of the list, and I have defined that to be over x values from negative pi to pi, y values negative pi to pi. So that is the first element, that is the first function. So that's that. And the second element of this list is g, and I put that in a local range also. So I have the function g and the values of x and the values of y, and everything else is outside the list used to plot. So the mesh lines, color, and the grid, they're all outside of the expressions that we wanted to plot. Could we do the same thing with a lambda function? So let's take something simple, such as h x comma y, and we define a lambda function. Oh, sorry. We'll define h as lambda, and we're going to specify two variables, and I'm going to go for u and v, and inside the lambda function I'm going to specify u squared plus sine u times cosine v. So that is my lambda function h. So let's try to plot the function h. So plot h, and we have to be careful because we can't use x and y because the values or the variables in the lambda expression are u and v. So it has to be u defined between negative pi and positive pi, and v defined between negative pi and positive pi. Let's get rid of the mesh. I'm not a fan of the mesh, so going to get rid of that, and the grid will do 30, 30. And that is our lambda expression, and you can see that it automatically populates up here that it is a lambda function that we defined. So suppose we have this h, and hypothetically speaking, let's just say that h that we just plotted right here is not in the regular rectangular coordinate system, rather it happens to be in the spherical coordinate system, and we want to change that and bring it back to rectangular system. So what I'm going to do is we'll take the same function h, but I'm going to define it as p and lambda, and I'll define theta and phi. Those are the coordinates that we have for the spherical system, and I will define it as theta squared plus sine theta times cosine of phi, and I'm going to plot 3D, and we want to plot p, specify ranges for theta and phi. So theta would be defined between negative 2 pi, or we defined it as negative pi to pi, and phi will be defined between negative pi to pi. Let's get rid of the mesh lines. Put a grid, and I'm going to add something called transform xy, and the parameter to pass here would be spherical to xyz. So we're assuming that p is defined in the spherical coordinate system, and we are bringing it back to the rectangular coordinate system. Forgot a percent. And that is the picture that we see. So this is nothing great or interesting because I just arbitrarily picked a function, but we changed systems, we changed coordinate systems, we left spherical coordinate system and we brought it over to rectangular, so that's what it's going to look like. Um, so if I take the same function, but this time I'm assuming that P is defined in the polar system. If you took Calculus 3, you should probably know what the systems are. If not, a quick Google search um, or YouTube search would give you tutorials on the coordinate systems. And I'm going to do transform xy. Here I'm going to specify polar to xyz. Perhaps it's polar to xy. It is polar to xy, I'm sorry. So, and that is the shape that we get. So, sort of is interesting. I didn't expect this, but so you can see I am rotating the 3D image to get at different views, but I could come up with an individual or a specific view by adjusting two parameters. Those are called the azimuth and the elevation. Now, this requires a lot of tinkering, so let me show three different cases here. I will take the previous plot and I'm going to specify elevation. It's 45 and azimuth is 30. Oh, I have to put it in square brackets here, I believe. Let's try it one at a time. I think it's elevation. Yes. So this time you see a picture of that sort, and I am going to find 90. Oh, probably it's outside the range. Let's do 10. Ah. And we are looking at a different side of the surface, and I could change that to 180 degrees and we will get a different view. So with a bit of tinkering you'd know exactly what the elevation and what type of a view you would get at a particular elevation and an azimuth. If you are not able to recognize this, you can always go to Google or YouTube and look up perspective views, and typically they are defined in terms of the parameters elevation and azimuth. And if you get an understanding on that, then you would know what values to put in exactly. So the key being elevation and azimuth are used to get specific views of the 3D surface that you have, but you could always rotate it here. I never found a use for these two parameters, neither in Maxima nor in R, because we have the flexibility to turn things around and save the picture as we wanted.